Okay. All right. So I will continue with Hormander's theorem. There seems to be too much of Hormander's theorem here, but the point I want to make is all these Hormander's theorem are based on the same idea as Dor pointed out, which is the positive curvature term, right? So in the Hormander's theorem that we are going to do today, and most likely it will flow over into tomorrow because I have too much notes here, but the curvature term is of a different nature than the one that Dor showed with the line bundle. So it's the curvature that resides on the boundary as pseudo-convexity. But ultimately, the mechanics of the proof and everything are basically the same. So we will. So today we want to do this Hormander. Let me state this right away. So where is this? I need to write bigger. So let now omega in Cn, and you should compare closely with what we saw in one variable. Be right now I will just make it smoothly bounded, although it is not really needed. Smoothly bounded and pseudo-convex domain. This, of course, is completely unnecessary in one variable because everything is pseudo-convex, but now this is crucial. And phi in C2 omega bar. So if you remember, when we did one variable, we did not insist that the function was smooth up to the boundary, but now we are doing that. Okay. Real valued. This is a strictly plurisubharmonic function. It's contained in the definition of plurisubharmonic, but strictly. Once I will write plurisubharmonic. And let C be the infimum of lambda 1 of A, where A belongs to omega bar, where this lambda 1A is the smallest eigenvalue of the Hessian of phi. This is obviously greater than 0, right? Strict, and we have come. We'll assume C greater than 0. All right. So these are the hypotheses, and the conclusion is exactly the same as before. For all G in L2 PQ omega phi, PQ forms integrable, square integrable against the weight e to the power minus phi, such that d bar G is equal to 0, and of course Q is greater than or equal to 1. There exists U in L2 PQ omega phi such that PQ minus 1, excuse me, such that d bar U is equal to G, and you have the L2 estimate. Norm of U phi, this is the norm in this space, is less than or equal to 1 over CQ norm of G square with respect to. So large parts of it look very familiar, right, from the one variable case. So what we are going to do, we are going to emphasize on those parts which are different. Okay, and thankfully Dror has covered lots of ground this morning, so I'll have to I can skip much of the stuff that I had written down. So let us clarify some of the terms that are used here. So strictly pre-subharmonic function. Okay, first of all, let's start with the pre-subharmonic function. Pre-subharmonic means it's a real valued function whose restriction to each complex line is a subharmonic function. Okay? So one can think of this as a complex analog of a convex function. What is a convex function of several variables? That means if you restrict to a line, you get a convex function of one variable. Here you have a function of several complex variables which you restrict to one dimensional complex lines, then you get a subharmonic function. That's what it means. Okay. Now, how does one detect subharmonicity or pre-subharmonicity? So, if you have smooth ones, so recall if phi in C2 omega is subharmonic, I'll just write subharmonic, then the Laplacian of phi is greater than or equal to 0. So what is the analogous way of seeing whether a function is plurisubharmonic or not? It's quite easy. So now suppose phi is plurisubharmonic, let's write in capital letters. Then if you look at the function, let's call it something u of z, which is phi of, let's call it zeta, a of b zeta, okay? So here a and b are vectors and zeta is a complex number. So then u is subharmonic. Okay. So let us try to take the Laplacian of this guy. So first of all, let's take the zeta derivative of this. So what do I get here? Zeta derivative of u of zeta. That gives me something like, by the chain rule, d phi d. So this, morally speaking, is a function of this and the conjugate, but right now we are differentiating with respect to the holomorphic coordinates. So d over dzj at a plus b zeta, and then you differentiate this guy, that gives you simply bj. And now you differentiate again, and then I am not using the summation convention, so I'll sum this from 1 through n. And then you differentiate again with respect to zeta bar. That gives me that the Laplacian of u zeta is the summation over j and k range from 1 through n, d square phi dzk bar dzj at a plus b zeta bj bk bar. Right? Is it clear? So this is, so in particular, since Laplacian of u at 0 is a non-negative number, it follows immediately that the Hessian of phi acting on the vector b is greater than or equal to 0. So Hessian at a, so I don't know where I want to put the a, let's put the a here, okay, where, so the Hessian of a at phi is the matrix d square phi dzj dzk bar, okay? And you think of this as a bilinear form acting on, defining a bilinear form acting on the vector b. Is that clear? So therefore, the condition of plurisubharmonicity is precisely that this matrix, this Hermitian matrix, right? It's a Hermitian symmetric matrix, is positive definite. And therefore, it will have real eigenvalues, and this lambda 1 is the smallest of them. Okay? And C is the minimum value of that. If omega were bounded, I could probably say C is greater than 0 anyway, but anyway, I'm assuming that this is greater than 0, and then this one. Okay, let me see if there is any other thing I need to explain here. I also need to tell you what these spaces are, but these have already been defined by Dror. right? And let us quickly see how things simplify a lot in this very, very simple and basic situation. So, since the metric is just the Euclidean metric, right? Those Gij's are just the identity matrix. So, therefore, the pointwise norms of any tensor is just the sum of the components each squared. So, for example, yes, please. Because I'm going to compute the adjoint in a few minutes. Okay, so and there you want to integrate by parts on the, you have a boundary term, so you need phi to be defined there. It's not the formal adjoint. For example, I would need the condition. I mean, this has already been done by Dror, but I'll rederive in much simpler terms the condition that that a form smooth up to the boundary belongs to the domain of Debraj star. So there you will need to integrate on the boundary, and then you need some phi, right? Yeah. Yeah, actually, I didn't do. Yeah. But Dror only did the compactly supported once. But for this theorem, I do need things up to the boundary. Absolutely. So that kind of result can be actually reduced to this by this Alaoglu kind of argument sometimes, right? And also actually Dror is, I think, going to discuss this. Yeah. Sure, no problem. Yeah, that was very illuminating. So of course these manifolds are highly non-complete, so they have boundaries. Okay, so they have,
yeah. Sorry to interrupt again, but this actually always has a complete Taylor metric.
Any pseudo, but we are not using that. We are just using the metric coming from CN. Okay, and as I pointed out, that metric results in quite a few simplifications. For example, those pointwise norms are now just the sums of the squares of the components, right? And so on, right? And this is okay. All right, so I think I explained that. Now I come to the computation of adjoints. So, our first Debraj operator, so there are two Debraj operators as Dror pointed out. The first Debraj operator is from L2. One more thing. So we will assume we only consider the case in which p equal to 0. Same thing, same reason as once you know this, the others are just there. Well, I could also have done p equal to n, but in, I think, domains in Cn, p equal to 0 is much more natural and easily understood. It's the same thing, yeah. Okay, so now you want to see this Debraj operator from 0q of omega phi, to L2 0 q plus 1 omega phi. Okay, so this is maximally realized. That is, the domain of this operator is precisely those things 0q such that the Debraj is also 0 q plus 1. So, by the general theory that we have been using for several days now, there exists a Debraj star operator, and by convention I put the phi in here, but in Dror's notation it would not appear. So I need to get a handle on what this is. So let's do that. So for simplicity, let us just consider, let us do the computations for q equal to 0, and I will state what happens if you have higher q. It's not really that different. I'll also need Stoke's theorem in a guise, which is integration by parts. So let me very quickly recall some formulas. Okay. So if I have a domain omega with a defining function rho, so omega is rho less than 0, I will always assume that d rho is identically has identically one magnitude along the boundary. Okay, this is of course always possible, And we have the following well-known formulas for, so if omega is in Rn, for example, I know that du over dxj of dv over omega, this is the integral over the boundary. This is the fundamental theorem of calculus for this domain. This would be u times you take the the unit normal vector field to this, the jth component of that, and integrate with respect to the induced surface measure. And that is the same as, because this rho has been normalized to 1, this is exactly the same animal as u d rho over d xj d sigma. And there are variants of this which are very useful. Another one that is quite useful is integral of du over dz bar or dzj bar now of omega dv. So it's just a linear combination of this and the I times that one. So therefore what I'm going to get is integral over the boundary of omega of du, there's no u anymore, u times d rho over dzj bar d sigma. And finally, I have integration by parts. Okay, so instead of one function here, I put two functions. So integral over omega of, so which one we want to put first? Let's put this one first. Du over dzj bar times v dv. So this is a function and this is the Lebesgue measure. So what is that? That is integral over omega of, you first take d over dzj bar of u times v, and from that you subtract what you want to subtract, which is in this case d over, this is u times dv over dzj bar, okay, dv, and that leads to the very important but elementary formula that this is equal to minus integral over omega u times dv over dzj bar dv, plus now apply the second formula to this one. That gives me integral over the boundary of omega u v d rho over dzj bar d sigma. Okay? So that is Stoke's theorem as we will need it. So for q equal to 0, let us now look at d bar u v with respect to phi. So what is that? That is therefore, okay, so here of course u is a function, so without loss of generality I will take smooth up to the boundary, and v is a one form, 0-1 form. I can write v as sum of vj dzj bar. Okay. All right. So this, by definition, is nothing other than the sum j going from 1 through n, integral over omega of du over dzj bar, this vj bar, e to the power minus phi dv, right? By the inner product, so all the gj's and all the other stuff in Raw's formulas have collapsed to this. Okay. And now you use what we saw there. So this leads to two pieces. One of them is familiar. So the first one you get is integral over omega of u times, okay, so now I have to be careful in writing this, minus e to the power phi d over dz vj vj e to the power minus phi, and now I correct this by putting e to the power minus phi dv. I just skipped and the bar and a sum here. Okay, now where do I put that? I'll put the sum over here. All right, and then I'll have the boundary term. Okay. Now what is that? That is going to be u times summation, I'll be careful this time, j going from 1 through n. So I put the bar also, therefore, Vj d rho over dzj e to the power minus 5 d sigma. Now let me step back and see if this is correct. I think this is correct. Okay? So this is what you get if you integrate this by parts. And this, you already know what this is going to be. This is going to be u d bar star phi v. And this is the boundary term. And this therefore must vanish if v belongs to the adjoint. Okay? So if v is C infinity 0, 1 omega bar intersection the domain of d bar star phi, this guy over here must be 0. If this is not 0, I could take a u which is large on the boundary and become smaller and smaller in the interior. So the L2 norm will go to 0. Right? However, the integral itself will depend only on the values on the boundary, which shows that the mapping that takes u to d bar u v is not bounded. So therefore, so this is an if and only if condition. So let us actually put it that way. So this is if and only if summation Vj d rho over dzj. A very, very important fact. So what this is saying is that if you look at this form V, okay, which you can think of as a vector, right? We are in Euclidean space. Then this is sort of the 1, 0 normal. The 1, 0 normal component of V is 0. So this is sort of like a Neumann type condition. And this characterizes the domain of d bar star phi. Okay, so this is something that we know. Let's see what we have next. Okay. Yeah, I need it in higher degrees also. So let me write that down. Higher degrees, exactly the same argument. So V is in C infinity 0 q omega bar intersection domain of d bar star phi. If and only if for all k which are multi-indices of length q minus 1, we have summation vjk d rho over dzj equal to 0, j going from 1 through n. So here these are the alternating coefficients of the forms. Okay? So I take this 0q form, I write it in such a way that the coefficients are alternating based on the indices, and this is the condition that you will get. So this is what it is. And of course, we also have a formula for d bar star. So for such a thing, and that formula is over here, d bar star v is given by summation j going from 1 through n minus e to the power phi d over dzj e to the power minus phi vj, which is exactly, if you want, the sum of d bar star j vj, where this is the operator that was introduced a few days ago. Key? This is only for one dimension. Yeah, right. Yeah. I'm going to write it there. Yeah. And okay. And d bar star v is now given by. So this prime means we are just adding the over increasing multi-indices. So you add over increasing multi-indices k of length q minus 1, and you have d bar star j vj k. Okay, so that's how it looks like. We are going to concentrate on the 0, 1 case, which already shows the basic features of this problem. So, okay. All right. other 0, 1 derivative operator. So this is the covariant derivative nabla bar. Okay? So this nabla bar, what does it do? Okay, it basically these tensors, they are given in terms of the standard basis of the forms and vectors. All it does is differentiate all coefficients. Okay? So for example, nabla bar of take a function. This is just a function. This is basically the same as d bar f, which is df over dzj bar dzj bar. Okay, and let's do this to a one form. So nabla bar of, let's say, alpha k dz bar k. We are only going to be interested in forms with anti-holomorphic indices. So this is summation jk excuse me. D alpha k over dzj bar tensor d zk bar, right? And so on. So that's what happens here. So it's very simple. So basically you take all possible bar derivatives. That's what it is. So so I can also realize this. This gives rise to maximally realized Hilbert space operator between some spaces of tensors. You know, I don't have any separate notation for that, but it's something like this, right? So for example, there is one such operator, nabla bar, which goes from L to 0 Q of omega to, now this space doesn't have a name, but I might want to call it something like L2 sections over omega of, so how would I say this? So then I want T star 0, 1 of omega, tensor these 0Q forms, which are therefore wedge Q, T star 0, 1 omega, right? So something like that. And therefore it has its own adjoint. Okay? Therefore there exists an adjoint, and I am kind of afraid to write this again, but it goes in the other direction. And there is the connection Laplacian, or the Bochner Laplacian, okay? So which was introduced. Okay? So if you really want to understand this, you might want to calculate what this is, okay? Which I am not going to do, but I am going to do something which is very important and interesting. So there are theorems, there are propositions, there are lemmas, and now we have a trick. So with the notation that we have set up here, we have the following. So suppose that alpha is in C infinity 0 Q of omega bar, intersection, and note this very carefully, domain of d bar star. Okay. Then, so I look at this energy form kind of thing. So I can't immediately say that this is, I would be very happy if I could say that this is the same thing as nabla bar alpha squared. That would be the case if I had taken an alpha which belonged to the domain of nabla bar star, right? Then I can integrate by parts and the boundary term disappears. Is that clear? However, here I will still have a boundary term, but that boundary term is very, very interesting. And let me write it down first in its coordinate form. So B omega summation length of k is q minus 1 primed, then j going from j and k going from 1 through n, d square rho dzj dzk bar alpha j k alpha little k big K bar, and then I probably will erase this anyway, e to the power minus 5 d sigma. So this part, this is first of all, this is a familiar friend of ours. What is this? If you take rho and you take its complex Hessian, that matrix is representing the Levy form, right? So this here, so let me rewrite this. So this thing is therefore the thing that was easy to understand, plus here we have the integral of the action of the Levy form. I should put some point or something, I'm just disregarding that. Action of the Levy form on this form alpha, which lies in the domain of d bar star, and we are integrating it. Is that clear? Yeah.
So the condition for the domain of d bar star is that this quantity here is zero.
Yes.
Defined
Right. So yeah, I was just going to come to that. Yes, but yeah. So okay, and that is a very important point that Rod made. If you now think of this as a vector, this exactly lies in HPM. So therefore, this is sort of an extension. So again, although we are talking about forms and vectors in Euclidean space, they are basically the same by so-called raising and lowering of indices. So this, yeah, I think I should have made this point right here. This condition is saying that this vector lies in HPM, the complex part of the tangent space. Okay? So therefore, here I have this natural action of the Levy form on these forms. Okay, so we will prove this. Okay? So you prove a theorem, I don't know what you do with a trick, maybe you trick a trick. So this is the trick. Okay, first you begin, let us begin by trying to compute. So alpha, okay, I think we can do it. Beta here is anything. I have not put, just smooth, that's all, the boundary phi. So what is this? This is by definition, okay, so another thing let us do is just concentrate on 0, 1 forms. So Q is 1, okay? Just make Q equal to 1 for simplicity. So this is integral summation over jk d alpha j over d zk bar beta kj. So here my notation is alpha is summation alpha j d zj bar, and beta, in anticipation of the way the indices behave, I have already written it as beta kj d z k bar tensor d zj bar. All right, but this I know how to deal with. This actually I have it exactly there. So what this leads to is, let me actually write it out. So this is the summation over jk of integral over omega of d alpha j d z k bar times beta kj bar e to the power minus phi dv. Okay. Now apply integration by parts, and let's hope I get it right the first time. So this is therefore the sum over jk, and put my parenthesis here, minus integral over omega alpha j, and then I have my familiar thing here. Let me just write it out, d over d zk bar beta kj e to the power minus phi dv, and I continue on to the next board. which is never a good idea, but sometimes we have to do that. Okay, and then you have plus integral over b omega. So let's be careful. Alpha j beta k j bar e to the power minus phi, and then d phi over d z k bar d sigma. And I need to close the parenthesis, of course. Okay. Is that clear? Just by integrating by parts. So the volume integral will definitely be nothing other than alpha nabla star beta. And let's look at this one carefully. So let's just write it down. So this is sum over jk integral over b omega alpha j beta kj bar. Let me change this order. D rho over dzk bar times e to the power minus phi d sigma. So not quite the way the thing is there, but now I think the trick itself comes in. Okay. So let's see. Somehow I have only part of my notes here. Doesn't matter. Okay. So you look at, now you use the fact, okay, so I used an arbitrary beta here. Now let beta be nabla bar alpha. Okay. So then what we get here is, so this equation here becomes length of nabla bar alpha squared is equal to alpha nabla bar star nabla bar alpha plus sum jk. Okay, now one has to be careful. So therefore, beta, so beta is given by therefore sum of, so alpha was alpha jk, so d alpha j over d zk bar, d zk bar tensor d zj bar. So therefore, what I get here is summation over jk integral over the boundary of omega alpha j, and here I will have d alpha j, over d zk bar. Yes, that's the only thing I need to replace. D rho over d zk bar e to the power minus phi d sigma. This is what I get. There's a complex conjugate over here. Yes, thank you. Yes. So all I need to do to complete this thing is to rewrite it in the form that you see in the statement of the trick. So and let's do that. And that requires a kind of interesting insight. So we know now that alpha belongs to C infinity 0, 1 omega bar intersection the domain of d bar star. What does that mean? That simply means sum of alpha k d rho over d zk bar, there's no bar here, I'm going to put it now, is 0. Okay? As you can see, here I have something similar, so I will bar this whole equation. Barring this is just bar, and I'll put a bar here. Okay? So if you look at this function now, let's look at this function f, which is sum over k of alpha k bar d rho over d zk bar. So this is a smooth function up to the boundary, and f is 0 on b omega. So you have a smooth function which vanishes on the boundary. However, the boundary is defined by b omega is nothing but rho equal to 0. So it follows, therefore, that there exists a smooth function h such that I can write this f as h times rho. Everybody is familiar with this argument involving fundamental theorem of calculus? Okay. All right. So in particular, so this is a general statement. So now let's let us differentiate this with respect to Zj bar. So this therefore turns out to be dH over dzj bar times rho plus h times d rho over dzj bar. Okay. So that is equal to h times d rho over dzj bar on the boundary. All right. Let's also compute df over dzj bar by direct differentiation of this equation. But df over dzj bar is by the product rule, and now I think you will see what the trick refers to, is the summation with respect to k of d alpha k bar over dzj bar, then d rho over dzk bar, plus another term alpha k bar d square rho dzj dzk bar. So therefore, combining these two, we see that on b omega we have the following relation, that this guy, okay, I don't need to write this down, this is equal to therefore h times d rho over dzj bar on b omega. Now we multiply both sides by alpha j bar, multiply both sides by alpha j bar and sum over j. Let's see what that gives me. What does that give me on the right hand side? So I multiply this guy by alpha j bar and then add over j, that gives me exactly 0, because alpha belongs to the domain of d bar star. And what does that give me on the left hand side? So summation over jk alpha j d alpha k bar over dzj bar d rho over dzk bar plus summation over jk alpha j alpha k bar d squared rho over dzj dzk bar. And if I have done everything correctly, I must have reproduced the term over here. I think I did that right. Is it clear? So the conclusion is, so the norm of alpha bar squared is the inner product, all are with respect to the metric phi, alpha d bar star d bar nabla bar star nabla bar alpha phi, and I replace the integrand there by what I find here. There's a negative sign, so minus integral over b omega alpha j alpha k bar. I'll just write it as rho j k bar with obvious meaning, e to the power minus phi d sigma, which is to say alpha nabla star nabla alpha is equal to norm of alpha, nabla bar alpha norm squared plus the Levy form of Levy form acting on alpha integrated on the boundary. And observe that this is actually a real quantity, so I can take bars and I will be left with this thing. Is this clear? So we have the trick. Okay? This is what we have. So now let us see what the trick tells us. So now let us get back to the Bochner-Kodaira formal identity, which Dror did this morning, which tells me that box, I'll write box phi in reference to the convention in this subject. Box phi is, so this is, there is no separate notation for this, but I presume I should also put a phi here, plus the curvature part, which in this simple case is just given by the Hessian matrix. So I think I'm calling it H phi, right? Acting on this. So let me just try to clarify how this acts as an operator, as a linear operator. So basically, for one forms, this is obvious, right? So if alpha is a one form, alpha j dzj bar, then H phi acting on alpha is simply another name for summation d square phi dzj dzk bar, and here you will have alpha j alpha k bar. Oh, there's no k bar, I'm not adding that yet, yes. So you will get this vector. And I'm not going to do this in general, otherwise you have to tag on the remaining part of the q minus, the remaining q minus 1 indices. Is it, or maybe I'll write that down, okay? So basically, if alpha is sort of like a higher degree form, alpha j dzj bar, where this length of j is q, then and beta is H phi acting on alpha. What that means is beta beta jk, I should not call it k perhaps, beta jl is summation d square phi dzj, or beta kl bar alpha j l. So that is the formula that defines it. In any case, this is the Hessian acting on certain forms. All right, so we have this Bochner identity, Bochner-Kodaira identity, and now let us see how that gives rise to the integral form of the identity. So this is therefore the Bochner-Kodaira Morrey Kohn Hörmander identity, which is obtained in the usual way. So you take alpha, which belongs to C infinity 0 q omega bar intersection domain of d bar star, okay? And now we compute Laplacian phi alpha alpha, and this side I will have nabla bar star phi nabla bar alpha alpha plus all are with respect to the phi metric, plus the other one, which is I'm writing as H phi acting on alpha alpha phi. Is that clear? What is this? I think Dror already explained what this is. Recall what nabla was. I think I forgot to make that precise. This is d bar star phi plus d bar star phi d bar. So therefore, let's compute them separately. Therefore, the left hand side is nabla phi alpha alpha phi. This is therefore two terms, d bar star phi alpha alpha with respect to phi plus d bar star d bar alpha alpha with respect to phi. First one, this alpha is smooth up to the boundary, okay? Then I can move this thing to the other side, which means that I will have here d bar star phi alpha norm phi squared, and this one is in the domain of d bar star. That's what I assumed. So therefore, this guy over here is d bar alpha phi squared. So the left hand side is completely clear. Okay. What do I know about the right hand side? Can I integrate by parts here? No. because I did not assume that alpha is in the domain of nabla bar phi star. Okay? However, I have my trick to help me. Okay? So therefore, the right-hand side, okay, just allow me a few minutes to complete this computation. The right-hand side is the sum of two things. It is nabla bar alpha squared plus integral over the boundary of omega L of alpha e to the power minus phi d sigma. I think I got that right. And then the thing that didn't change, so therefore I have now the full identity. Let me write it down. So for all alpha which do belong to C infinity omega bar intersection domain of d bar star phi. Observe that this, if it is an unbounded domain, we don't need to worry about integrability because this is by definition contained inside L2. So that is taken care of. I was getting a little worried here, but then I understood that was correct. Okay. So we have that norm of d bar alpha phi squared plus d bar star alpha phi squared is equal to nabla bar alpha phi squared plus the integral over the boundary of the Levy form evaluated on this alpha, which makes sense as Dor pointed out because they lie in exactly the correct space, e to the power minus phi d sigma, and finally I have h phi alpha. So this is the Bochner, Kodaira, Morrey, Kohn, Hörmander identity. Okay, all right. Now, at this point, till this point, we have been doing only integration by parts. We have not invoked any properties of the domain. Okay, but what did we assume about the domain? I have removed that assumption, but that assumption is that it is pseudo-convex, which means that this thing over here is a positive semi-definite Hermitian form, which means this is greater than or equal to 0. This is anyway greater than or equal to 0. Okay? So therefore, this implies that norm of d bar alpha phi squared for the same alpha plus norm of d bar star phi alpha squared phi is greater than or equal to the one surviving term, which is h phi alpha alpha phi. Is that clear? But what did we assume about the Hessian? We assumed that it was bounded below by C, right? We assumed that it's the lowest eigenvalue of the Hessian at any point was at least C. In this case, I don't need to worry about domains and stuff because this is in n dimensions. So by hypothesis, this h phi of alpha, alpha is actually greater than or equal to c times the norm of alpha phi squared. Right? So therefore, if you put that wisdom in here, okay. So let us write down this thing here because that is the thing which will lead to n. So it follows for all alpha smooth up to the boundary and in the domain of d bar star, we have the following formula: d bar star alpha norm phi squared plus d bar alpha norm phi squared is greater than or equal to this constant c times norm of alpha phi squared. So this, therefore, is the basic a priori identity, a priori estimate, thank you, of L2 theory on domains. Okay. I think I'll stop here, okay, because to convert this into an actual estimate will require discussion of the density of forms. Okay. Thank you very much.